Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Process Technology Part 1 Module 24. Just a quick recall of what we did in the last lecture. We were talking about the various issues related to solidification of molds, particularly the fact that what difference will it make by the presence or absence of a chill, and we also found out that there is a dendritic growth which happens because of a change in concentration across the solid liquid boundary, as in the solid phase the amount of liquid amount of solid that is really allowed may be lower than the liquid phase. The solubility of the solid phase therefore may be different in the solid as well as the liquid phase. So, having said that, now we would like to just understand the consequences. So, the freezing pattern of a chilled and ordinary mold are shown right about here. This is the freeze diagram. As you can see here, this is the distance from the mold face. Therefore, this line here right here really is the face of the mold, okay. And you can very well see that the face of the mold is completely frozen at the point B. So, there is a liquid line which is somewhere here. This is the liquid part. This part here is the liquid plus solid part. So, therefore, there is a partial solidification, partial liquefaction, and then finally the whole mixture freezes here to the complete solid state, as you can see here at the point B. So, between this O and B, the available phase is a mixture of the liquid and the solid, and beyond B there is a complete freezing. So, therefore, this all portion right here are the solid portions of the mold. So, in this figure the solidification starts at the center line of the mold before the solidification is complete even at the mold phase, obviously, because I think we had illustrated earlier that the dendritic growth structure would take place from the mold phase onwards, and therefore, you can say that the center line of the mold may start the solidification. So, somewhere let us say if this is the mold center line, and you can see the start of the solidification point here where there is a solid plus liquid formed here, it is much before the point B where complete freezing has happened actually. So, in the chilled mold, on the other hand, due to rapid heat extraction, this line or this region of the solid plus liquid gets narrowed down, because of which obviously the center line or the mold phase would have completely solidified before the center line would start the solidification. Look at the point, for example, O and B are more or less similar. So, it is an immediate sort of freezing of the mold phase, and then the point where the solidification would start to happen on the center line is at A. So, A is far beyond in terms of time. So, it is at a much later point of time in comparison to O and B. So, a narrow liquid solid zone quickly sweeps across the molten metal, and the difficulty of feeding a given alloy in a mold is expressed by the quantity called center line feeding resistance. I think this we had done in the last lecture as well. So, obviously, if there are solidification fronts which are formulated till and until the mold phase is not even solidified, it is very difficult for the liquid metal to kind of feed in, because it has to pass through all these different solid boundaries. Okay. So, think of it, the liquid is coming through the gate region into a mold, and it is facing so much of solidified front as it moves from the mold phase onto the inner center line of the mold. So, there is something called center line feeding resistance which would develop, and typically this is the time interval between the start and end of freezing at the center line as a percentage of the total solidification time of the casting. So, if supposing there is a start and end of freezing here at point A, the center line starts partially freezing, and there is a solid plus liquid mixture developed here till and until it ends at the point C. So, this particular interval of time, whatever it takes, as a function of the total solidification time, as a percentage of the total solidification time, which really is the point where the solidification has happened starting O all the way to the point C where the end of freezing cycle has happened. So, AC by OC, AC is this much time, okay, and OC is the total time of freezing, so that the whole casting can be completely frozen. So, this expressed as a percentage is CFR. So, obviously, if this time interval were narrow, for example, in a case of this chill, time interval becomes lesser. So, the total CFR which would be typically obtained would be lesser, because obviously this time interval AC is much lower in comparison to this where the chill was not used. So, this is a case where there is a chilled mold which is there. So, chill has definitely a lot of advantages, because it prevents the dendritic growth as well as reduces the centerline feeding resistance. So, having said that, now if we look at what really is happening for in an event wise basis, the rate of solidification can be really calculated as a function of what is the heat transfer across the mold face. And obviously, in the design itself of the casting, we had discussed that there is a reservoir of liquid metal called riser, which is actually used to compensate for the shrinkage that takes place from pouring temperature up to the solidification temperature. I think we had illustrated very clearly that as the liquid metal is poured inside the mold, there is going to be a change in the volume of the liquid metal per se. There is going to be a change because the liquid metal solidifies. So, there is some change of state from liquid to solid, and then obviously the solid contracts, because the temperature comes from the freezing temperature all the way to the room temperature. So, in order to do this compensation for this shrinkage, there is always a reverse flow which is generated, because riser on one hand is an indicator whether the mold has been filled, and on another hand is basically a reverse flow generator which would create no shrinkages, or which would reduce the shrinkages by a backflow of the material from the riser into the mold. So, in this respect, grey cast iron is an interesting exception where solidification occurs in two stages. The shrinkage associated with the first stage may well be compensated by expansion that takes place during the second stage, as such a riser may not be necessary. And to ensure that the riser does not solidify before the casting, we should have an idea of the time taken by the casting to solidify, and therefore, the time of solidification and how you estimate it is also an integral part of the designing of the casting as to where the riser exactly would be placed based on the time of solidification. So, you can place the riser in a judicious manner, and if your correct time estimate can be obtained of solidification up to a certain distance from the mold face. The heat released as a result of cooling and solidification of the liquid metal passes through different layers. Let us look at what happens here. So, you have on one side the distribution of temperature across the mold face. So, this right here is the mold. So, this right here is the mold, and you can see that there is a temperature drop in the region 1 in the between, let us say, in the air. There is one temperature drop region 2 in the mold itself. So, this is actually the outer surface temperature of the mold, and this is the theta ambient, which is actually the temperature of the environment in which this mold is present. You have one temperature across the mold face. So, you have a higher temperature at the mold face here. There is obviously a solidified metal region. So, there is going to be a change of state over this region right here, and there is going to be from the solid region almost a difference in temperature from the mold wall all the way to the freezing point of the liquid theta f, where the state conversion would happen between liquid and solid, and beyond this it will be liquid metal. Obviously, liquid metal also, as it is more and more away from the mold, would have different temperatures. So, the temperature distribution here is really the resistance that the air, the ambient environment in which the mold is present, offers to take the temperature down, there is a resistance offered by the mold itself. So, there is obviously from the face to the wall, I mean, so from the mold wall all the way to the the outside face of the mold, there is some kind of drop in the temperature because of the resistance offered. There is of course a resistance offered by the solidified metal which is at the mold face. So, there is going to be some change in the temperature, some small minuscule change in the temperature from the at the mold face itself. There is also going to be a change in temperature beyond the solidified metal all the way to the liquid metal liquid solid interface, and we assume that the liquid solid interface is at the theta freezing temperature, beyond which again there would be a change in the temperature in the liquid metal itself. So, the resistance of the to the temperature here is offered by the metal, here it is offered by the solid metal. Here again it is basically a function of the way that the solid is coupling with respect to the mold wall. There may be a small film for example formulated, and we will do all these cases independently when we do problem examples. There may be another case here where the mold itself is sort of thermal inertia, it provides thermal inertia, thermal resistance, I am sorry, and then it basically again takes down the temperature, and then obviously the air around the ambience around the mold wall which is also responsible for the same. So, the thermal resistances which govern the entire solidification process can be summarized to be those of the liquid, the solidified metal, the metal mold interface, the way that the solid film is coupled with respect to the mold wall. In case the mold wall is rough, there may be an air film in between. In case supposing there is some kind of a proper, like in case of aluminum mold and pressure die casting, there is a proper boundary between the metal to metal which is formulated. There also the estimate would be completely different. Then the mold itself that provides the resistance and the ambient air. Okay. So, the 5 different regions are indicated by numbers 1 to 5 in this curve here, and obviously the solidification process is quite complex, especially when complex geometry, freezing of alloys or temperature dependence of thermal properties is considered. So, having said that, let us now look at a simple example of how to calculate the temperature loss. Let us say during solidification of a large casting in an insulating mold like the one in sand mold for example, this is a sand mold, or maybe in even investment casting, almost the entire thermal resistance in this particular case is offered by the mold itself, because the sand itself is a great heat sink. Okay. And so, therefore, whatever resistance is maximum offered is offered by the mold. So, the analysis we give computes the freezing time by considering only the thermal resistance of the region 2 of the graph shown earlier. So, this particular region where it talks on one side the ambient air, on another side the liquid metal, and there is a mold resistance which is the principal thermal resistance being considered. So, let us assume some boundaries here. We consider that the mold face of AB is, as shown here, is held at a temperature theta freezing, where the liquid is getting converted into solid. So, that is called the freezing temperature. The large mold initially at a temperature theta 0 is assumed to be extended all the way up to infinity in the x direction. So, you can assume this mold to be very large in comparison to dimensionally, in comparison to the casting. The casting may only be a very small slab in comparison to the width of this sand mold. So, extends to infinity, and at time t equal to 0 we assume the liquid metal to be at temperature theta p, and it has been poured into the mold. The moment it meets the face, it comes to the temperature theta f, which ensures that it starts to freeze, and then solidification front moves ahead with as a function of time, as a function of distance from the mold as well. So, we assume that the metal just in contact with the mold face solidifies instantaneously. In other words, the temperature of the mold face is raised to the freezing temperature of the solid liquid boundary time t equal to 0, and is maintained at that value till the completion of the solidification process. So, let us look at what is the temperature distribution in such a case which would happen. Okay. So, the way that we do it is to try to solve the heat transfer, one dimensional heat transfer equation. Delta 2 theta by del x 2 is 1 by alpha del theta by del t, where alpha seems to be the thermal diffusivity. So, theta is basically a function of x and time t, and this is the temperature, this is temperature, and we want to first try to solve what is the variation or what is the function or variation of theta with respect to x and with respect to t by solution to this equation. We already know that the boundary conditions allow this heat transfer at x equal to 0, the theta becomes equal to theta freezing, okay. And you can say that at x equal to infinity, that means the mold is infinitely large, the theta may become equal to the theta ambient or theta at infinity, you can say, okay. So, that is how you do this calculation, or that is how you represent this, and then we assume that theta 0 is the ambient temperature in which this whole heat transfer is taking place. So, having said that, now let us actually use a similarity variable method for solving this equation. So, we will create a variable here called eta, where eta is basically x by twice root of alpha t, and eta is a dimensionless variable. This is a dimensionless variable. You can compare the distance units with respect to the alpha and time t. So, we first try to find out the del theta by del t in terms of del theta by del eta times of del eta by del t, okay. And then on the other side we derive del theta by del x with respect to del theta by del eta times of del eta by del x. So, from this equation right here, equation 1, del eta by del t is equal to x by twice root alpha minus half t to the power of minus 3 by 2, and which again means this is equal to x by twice alpha t whole under the root times of minus half or minus 1 by 2 t. So, I can say that del eta by del t is nothing but minus eta by twice t. So, in other words, this expression right here changes to del theta by del eta times of minus eta by twice t. Similarly, we would like to find out the expression for theta or del eta by del x. So, the del eta by del x is 1 by twice root alpha t, and this can be again represented as eta by x, and so I can say that similarly in this case del eta by or del theta by del x becomes equal to eta by x del theta by del eta, okay. So, this can be equation 2, this can be equation 3, and we need to now find out the second derivative of this. So, we just do del by del x of del theta by del x, which makes sure we have del by del x of eta by x times of del theta by del eta. So, again we apply the chain rule here. So, we have del eta by x times del x times del theta by del eta plus eta by x del by del x of del theta by del eta, and we can now change or differentiate this guy right here, because obviously this eta by x is only a function of time, as you could see here, and so this would go to 0, and we are only left with eta by x times of del by del eta del by del x times of, or del by del x of del theta by del eta. So let us just again apply the chain rule here. We have del by del eta of del theta by del eta times of del eta by del x, and del eta by del x again comes out to be equal to n by x. So we are left with the term n by x square del 2 eta by del 2 theta by del eta 2. So having said that, now let this be regarded as equation 3. So from equation 2, 3 and I am sorry, this is equation 4 and 4, we can actually put the value of del 2 theta by del x 2 into the heat transfer equation right here, and same we can put the value of del theta by del eta from 2 back into the heat transfer equation here. So we are left with eta by x square times of del 2 theta by del eta 2 equals 1 by alpha times of del theta by del t, which is actually equal to del theta by del eta times of minus eta by 2 t. So we have, putting this value here, one by alpha times of minus eta by 2 theta times of del theta by del eta. So having said that, it is little simpler to solve this equation, and what we can do then is we can actually try to see what eta was. So eta was estimated from the term x by twice root of alpha t, and if I just wanted to solve this equation that I formulated, let us call it equation 5 here, which is square of eta by square of x del 2 theta by del eta 2 becomes equal to minus eta by twice alpha t times of del theta by del eta. Okay. Further, this eta goes away, okay, and we are left with eta by x on one side, eta by x square on one side times of del 2 theta by del eta square, and this becomes equal to minus 1 by twice alpha t del eta by del theta by del eta. So obviously square of eta can be represented as x square by 4 times of alpha t. So if I were to just substitute here or convert this equation here, we get del theta by del eta square times of eta equals minus of x square, let us put it twice x square by 4 alpha t, and this term right here is eta square. So it is minus twice eta square, okay, and this can be estimated as del theta by del eta on this side. So we are now finally left with a term or an equation of the form completely converted into the similarity variable eta here, okay. So everything in terms of eta, and I call it del 2 theta by del eta 2 equals minus of twice eta del theta by del eta. So this is the ordinary differential equation with one variable, and we would like to just solve it by integrating again and again. So let us say if we assume del theta by del eta to be a variable or a value equals to, let us say, y here. So, we have del y by del eta equals minus twice eta times of y. Okay. So, we can easily solve this by taking y on the other side and making it equal to twice eta del neta, and we integrate on both sides. So, after integrating, this becomes ln y, and this becomes minus twice eta square by 2 plus the constant of integration c. So, in other words, this can be written down as ln y equals square of eta minus plus c, or y becomes equal to some constant c2 times of e to the power of minus eta square. So, let this be equation 6. So, as our y is actually equal to del theta by del eta, which can be written down as c2 e to the power of minus eta square. So, we can find out a solution for now theta as a function of eta, and eta basically involves the variables x and t, and I am going to do that. I am probably going to close this module now in the interest of time, but in the next class I am going to actually try to find out what is this theta, considering all the temperature boundary conditions, etc. So, with this I would like to end this session. Thank you so much.